Go ahead.
Okay. Okay, welcome, Julie Symons from University of Antwerp. Um, and thank you for accepting our invitation to talk on solving the curvature problem for TDG categories. Thank you.
All right. No, thank you, Javier, and also Najib, I should say, for the invitation. Okay, today I will talk about the curvature problem, and in particular, our solution to it for TDG categories. This is joint work with my supervisors, Wendy Lowen and Michel van den Bergh. And it's also together with Francesco Genovese, and it's contained in this preprint right here. Now, I like an informal setting, so if you have any questions or comments, just interrupt me and ask them during the talk, unless it will take like 15 minutes, because then we have some time issues. Okay, then I think I can start. So the talk consists of 3 parts, and the first one concerns motivation, which I think is very important. Okay, and I want to start by mentioning Kontsevich's homological mirror symmetry conjecture, which is sort of infamous at this point. And in this conjecture, he states that there should be an equivalence of triangulated categories coming from string theory in physics, where you have the A model, which translates into a Fukaya category, and the B model, which translates into an enhancement of the bounded derived category of coherent sheaves over a scheme. Anyway, we have an equivalence of triangulated categories, but Kontsevich moreover asserted that the deformation theories of these 2 categories should correspond, and thus people started to look at a deformation theory of triangulated categories. Okay. Now, as I think most of you will know, the structure of a triangulated category is insufficient for many purposes. They don't really reproduce, and in particular, we don't have base change functors available. Now, base change functors are crucial to have deformation theory available, as I will explain in a bit. And that is why we usually consider a richer structure lying on top of the triangulated category, which we call an enhancement. And we work with DG enhancements, so DG categories, which we then call pretriangulated because they're lying on top of a triangulated category. And I will actually briefly define them during the second part of the talk. But for now, since we're going to focus on the motivation, I will say something about deformation theory first. So deformation theory is an old topic, and actually there are many deformation theories depending on the type of object you want to deform. And I think this is best explained by looking at some examples. So you can consider an algebraic object, and then there is a corresponding notion of deformation. And I think, in my opinion, the easiest case would be that of an associative algebra over a field. So say we have an associative algebra A over the field K. And we also have an appropriate K-algebra morphism, theta, from R, where R is a K-algebra, to K. And appropriate means that it has some nice properties, but for one, it should certainly be surjective. Okay, then we can define what is called an algebra deformation. If something is unreadable, by the way, also let me know, of A along theta. And if you think about it, the data of an associative algebra is really just the data of an associative multiplication on A. So if we want to deform the algebra, what we want to do is we want to change the multiplication, because that's the essential part. And so an algebra deformation of A along theta should be an R algebra A prime, such that if we tensor by K over R, we obtain our original algebra A. So what we're actually doing is we're taking this multiplication on a K-algebra, and we're going to extend it to R multiplication on A prime, so that it is compatible by restricting along theta. And the theta shows up in the tensor product. Now, usually we will work with a fixed base change morphism, where instead of R, we take K epsilon over epsilon squared, so the dual numbers, and then the base change morphism just puts epsilon to 0. In this case, we speak of an infinitesimal algebra deformation. This really has to do with just viewing this as a thick point of order 2. You have like 2 tangents, yeah. Anyway, and then this definition with the tensor product just translates more or less into, well, an algebra deformation along this map from K epsilon over epsilon squared will just be an associative multiplication on A epsilon, such that, let me maybe call the original multiplication on A mu. Then we should have that if in mu prime we put epsilon to 0. So actually we just compose with this map theta that we obtain our original mu. Okay, so this is really how you should think of a deformation. You just change the important structure slightly. And then there's, of course, this third column that you all know very well, where I should put the Hochschild cohomology. So the Hochschild cohomology is indeed the cohomology of a complex, the Hochschild complex, and it consists for every natural number of a group. And it is also known to govern the deformation theory. And a specific instance of this is the fact that if you take the second Hochschild cohomology group, this will actually be in bijection to these infinitesimal deformations up to equivalence. So this is a bijection, 1-to-1. And as soon as you've understood this picture for the algebra case, you can actually do the same thing for a lot of other algebraic objects. And yeah, you can ask me about this map, but I think everyone here is familiar with it. So yeah, the condition of this being associative will be precisely what you get in the condition of being a Hochschild to-go cycle. So okay, we can do this for other algebraic objects. We can do this for a scheme over a field, where a scheme deformation is now a pullback, not under the tensor product, but under the fiber product. And then this is actually controlled by the first sheaf cohomology of the tangent sheaf. But if your scheme is quasi-compact and separated, which in practice is really almost always the case, then this is a direct summand of the Hochschild cohomology. So again, the Hochschild cohomology really governs the deformations. And yeah, we also have a linear category that we can consider, which is just a multi-object case of the algebra. A linear deformation is also defined via tensor products, but on the level of the Homs. And then there is a natural notion of linear Hochschild cohomology that is in bijection to these infinitesimal deformations. Same story for an abelian category. Think of modules over a K-algebra or coherent sheaves over a Noetherian scheme over a field. Then there is a notion of abelian deformation. We now don't use the tensor product, but we use the Hom, the right adjoint, because the tensor product won't preserve the property of being an abelian category, but the right adjoint will. And again, there is a notion of abelian Hochschild cohomology, but it's important to stress that these two are different. We can deform an abelian category linear over field as an abelian category or as a linear category, and the two are fundamentally different. So the Hochschild cohomologies, the complexes that govern the deformation theory, are also different. And hence the subscripts. Okay, and then there are many other algebraic objects that we can consider, but due to this homological mirror symmetry conjecture, for example, well, we are interested in triangulated categories, and as I said, pre-triangulated dg categories. So ultimately, we want to jump to the row of dg category. And if you have a dg category, there's again a natural notion of dg deformation, where we use a derived tensor product. And as you have tensor products, you also have a natural notion of Hochschild cohomology. And is this on my side? I guess not. Okay. The problem, however, is that we no longer have this bijection. And this is what we call the curvature problem. And I'm going to give this like a pink color. Okay, and this is not nice or not ideal. Okay. So the curvature problem was first studied by Keller and Lowen and Nicolas, and Lowen and Van den Bergh. And it can be stated in the following way. If we have a dg category, A, linear over the field K, then if we deform it using the notion of dg-deformation, then it might happen that we actually end up with something far more general, namely a CA infinity category. Now, I haven't actually defined dg categories, but very briefly put their categories that are enriched over cochain complexes. So the humps are complexes and have a differential. And of course, the differential squares to 0. Now, in the CA infinity realm, the differential does not square to 0. It squares to C, where C is the curvature. And this in general will not be 0. But this is, of course, problematic because all of homological algebra no longer applies. So no y-ball. And yeah, this makes these objects quite wild. And there are also a lot of CA infinity categories, meaning that lots of them will be very far away, far away from the geometric picture. Usually when we study triangulated categories, we depart either from a representation-theoretic viewpoint, it's like modules over an algebra, or from an algebraic geometry viewpoint, coherent sheaves, or quasi-coherent sheaves. And if we end up here, we might be too far away from actually tractable categories. So what does the curvature problem say? It says that, well, this dg Hochschild cohomology, it governs the C A infinity deformation theory of A instead of the dg deformation theory. And if you know anything about A infinity categories, this is because dg is too strict, but A infinity is, or C A infinity certainly is just too flexible, let's say. Now, what would a solution to the curvature problem be? And this is important because solution might not mean what you think it means. It means giving a reasonable interpretation, a deformation-theoretic interpretation of this Hochschild cohomology. So one that we can understand and one that we can work with. Now, it has been shown that in general, no universal solution exists. If you want to know more, I can give you a reference. But there is some hope. There are partial solutions available. And the following list is not complete, but I do want to mention some. I want to say something about Morita deformations. So this is due to Keller and Lowen in 2009, and also to Lowen and Van den Bergh in 2015. And here the idea would be to pick a smart representative of your Hochschild cocycle and try to get rid of the curvature that way and sort of change things up to Morita equivalence, of course. However, in general, this will not work. Then there is a recent approach by Lowen and Lehmann, who was a PhD student of Wendy at the time, but now is doing a postdoc. And this approach is very orthogonal in the sense that they sort of embrace the curvature. And they try to work with curved homological algebra, which is quite scary. But because they're considering curved infinity categories that show up as deformations of A, the curvature will be very small because it arises as an infinitesimal deformation. And you know, this E squares to 0. So there is still some hope because it arises that way. And then there is a third approach that I want to mention, and that is actually our work on TDG categories. And so since I'm still in this first section on motivation, let me also motivate our idea for this new approach. And the motivation comes from a theorem of my two supervisors from 2004 in their work on abelian deformation theory. Because usually, as I mentioned, we're interested in these geometric examples in the bounded derived category of an abelian category or a DG enhancement thereof, more or less the same thing. And in this case, there are very good indications that we can actually solve the curvature problem because they showed that the Hochschild cohomology of this DG category is actually the same as linear Hochschild cohomology of an associated linear category, namely that of the injective objects of the incompletion of A. And this incompletion is just a technical tool to ensure you have enough injectives, because you know finitely generated modules or coherent sheaves will not have enough injectives, blah, blah, blah. But this is great because if you think back to this table, then we've now jumped to this row of linear deformation theory, where everything works really well. So they translated it to something we can understand. And using this classic linear picture, they were able to give some reasonable interpretation at the time of this second Hochschild cohomology group, but they were unable to really formalize the notion of deformation that is sort of showing up. But this I will actually formalize later on. So just to maybe draw the picture of what they did with this theorem. So if you consider here this bounded derived category, then what the Lowen and Van Bergh did is they associated to it this linear category of injective objects. And so they now translated this to a problem in the linear realm. And well, here deformation story works really well. So we just stay within the class of linear categories. And then we can jump back. And because of their correspondence, we just, oops, this should be yellow. We just end up within this DG world. And that's how they solve the curvature problem, in the sense that we stay within this DG world, so everything is reasonable. All right, so now the aim was to generalize this to similar DG categories. So using this bounded derived category as the leading example, and also to the higher Hochschild cohomology groups. This is more of a byproduct. So we will be able to give an interpretation for all the higher Hochschild cohomology groups, which is quite nice, I think. All right, and that's this first part on motivation. Any questions so far?
Yeah, so
okay, I don't think so.
Sorry.
Yeah.
Yeah. So the injected object
No.
that you got there, that on the Bergh and Lowen, okay, they are all from the original.
Sorry, I'm not sure the rest can hear you, but
Hello?
The service.
Like a robot. Maybe you can
I'm
come
not sure if
closer
it's
to.
my connection.
Do you hear me well? Hello?
Yes.
Right. So that category of inch in A is the or It doesn't
I
matter.
think connection was
Like
very.
it is Julie's connection.
Okay.
Yeah, sorry. Yeah.
Maybe-
Yeah, but now I'm back. Now I'm back. Sorry, can
Okay.
you repeat the question?
Right. Yeah. So here in this process of Lowen-Van, so you have this category which is the injectives in A. These are injectives in the original category, or they need to produce these new injectives there. So
Yeah, if A itself will have enough injectives,
that
if A has enough injectives, you don't need to take the int-completion.
right.
That you can show, but you need to prove this. But
Yeah.
in general, you need the int-completion.
Right.
So the first result would be to go to the int, and then you can remark that actually, if you have already enough injectives, the Hochschild cohomology does not change.
Right. I see.
Yeah.
Right. Okay.
It's a good question. Yeah.
All right. Cheers.
Mhm. Okay. Any other questions? Okay. I don't think so. Yeah, I hope my connection remains stable. All right, then I think it's time I tell you about TDG categories because, as I said, our aim would be to generalize this leading example, and we're going to generalize to the class of TDG categories with some conditions on the T part. Okay, and I did not want to just give you the definition, but I wanted to sort of dissect the leading example. Okay, so we start with an abelian category linear over a field. Then we can consider, as always, the bounded derived category, which you can view as, well, you can take the bounded complexes over A, and you can quotient out the acyclics. Now, usually the derived category is actually defined by inverting the quasi-isomorphisms, but if you recall that the cone of a map is a cyclic if and only if the map is a quasi-isomorphism, then you can easily see that the two should be the same. Okay, so as I already mentioned, actually we want a DG enhancement. So I will put DG everywhere for now. And then I will actually explain what I mean by DG category. So first, because this is a quotient, it suffices to actually define a DG structure on this thing, which will then be inherited by this full subcategory, and then this thing will be a DG category. So let me just say something about the DG category CB DG of A. Okay, so as I already said, a DG category is a category enriched in complexes over K. So if you consider a K-linear category, then this will be enriched in K-vector spaces because the Hom sets will be K-vector spaces and the composition will be K-linear, bilinear. The same thing is going on when you're enriching in complexes. So your Homs now will be spaces, complexes, and the maps will be compatible with the differential. So if you want to define a DG category, then what do we need to do? We need to define for any two cochain complexes bounded in a complex in vector spaces that will serve as this Hom. And so what I put in degree n, so for any integer, we have a component, graded component. And in degree n, we put families, integer indexed, of maps from A to B, where each component fi goes from ai to bi plus n. So f0 goes from a0 to bn, f1 from an to bn plus 1, and so on. And then, of course, we also need a differential, a degree 1 map, because I'm working cohomologically. And so this differential going from n to n plus 1 takes this family fi and creates an object in the n plus 1 component. So now f0 has to go to bn plus 1. And there are two ways of achieving this. We can post-compose with the differential of b, pre-compose with the differential of a, and we take both options and put an appropriate sign due to the causal sign rule. Now you can check that this is a differential, so this is a complex. And this is what, this will be a DG category. And as I already mentioned, because of this fact here, that the parametrize category is just a quotient, we actually get a DG category, dg of A, okay. So note, by the way, that these squares don't have to commute, but if you take the kernel of such a differential, you will ask that squares commute. Now, given a DG category, so the Hom spaces are complexes, we can, of course, take the H0, which is the zeroth cohomology, so the kernel of the differential in 0 divided by the image of the differential in -1. And if we take the homotopy category of a DG category, what we mean is precisely this. We replace this Hom space, which is a complex, by the zeroth cohomology. And if we do this, we just obtain our bounded derived category. And so we call this lower bit the homotopy category. And conversely, we call this a DG enhancement. Okay. Okay, and so this is really the first thing that we have in the definition of a TDG category. We have a DG category over the field K called B. And so this is the B for our leading example. Okay, but there is a second bit, because of course we don't just want to deform any DG category, we want to focus on triangulated categories. So in our leading example, this dB of A is of course triangulated. And so the second part of the definition of a TDG category is a DG category B, such that the homotopy category is triangulated, ergo B is pre-triangulated. This you could view this as a definition of pre-triangulated DG categories. Okay, and so now you can wonder, is this sufficient? Well, it is not clear from this picture, but it is not. It might be that you have a pre-triangulated DG category that you deform, and you will still end up with a CA infinity category, and even complex group, you will not get rid of the curvature. So there is something extra that this leading example has that we really need. Okay. So this is what we have so far. Now, of course, in this bounded derived category, this abelian category A is important. You can embed it by viewing an abelian object as a stalk complex concentrated in degree 0. But you can also go in the opposite direction by taking the zeroth cohomology. And actually, you can view the zeroth cohomology as truncating below 0 and above 0. And these truncations, that is precisely the extra data that we need. Okay. They come from the so-called standard T-structure that you have on the derived category. And so I think most of you will be familiar with a T-structure, but for those that are not, a T-structure on a triangulated category is given by a pair of subcategories, smaller than 0 the isle, bigger than 0 the co-isle, and they should satisfy certain conditions. So for the derived category, you have a very easy one, where the isle just consists of all the complexes that don't have cohomology above 0. And then for the co-isle, you consider only complexes that don't have strictly negative cohomology. You can sort of use these two to split objects in your category. Okay, and so the third part of the definition would be so a DG category that is pretriangulated with a T structure on the homotopy category. And I want to stress that it's important that the T structure is part of the data. You can have multiple T structures on a triangulated category. And so as a TDG category, these two will be different. So you fix one. And this is not part of the definition, but in practice, our T structure will be non-degenerate always. So non-degenerate or bounded. And if you don't know what this means, just forget about it. Okay, things that should not be zero are not zero is sort of the main idea here. All right, and then the final bit of this second section is just me telling you again that this leading example really is a TDG category, but that there are other interesting examples out there. And a very easy one would be if you have a connective DGA. Connective meaning it doesn't have any cohomology above zero. Then you can also define a derived category in the same way as same way philosophically as you do it for in the classic case. There's always a T structure on this thing, also if you don't have a connective one, but in the connective case, T structure will be non-degenerate. And so this is a good example to also keep in mind. Okay, and then we can actually go on to the main results, unless there are any questions. Okay, I guess not. So, solving the curvature problem. I think for you it's also lagging, right?
Yes.
Or not really? Yeah. It's moving very slowly. Yeah, okay.
So in the
All right.
meantime, actually,
Yeah, cool.
no, you can go ahead. I mean, I would have questions at the end, so don't worry.
No, oh, yeah, okay. But do you feel like you won't understand as much if you don't ask them now? Because
no. It's about applications and stuff, so it goes to the end. No, that is.
Okay, great. Okay, so for the final part, I want to just mention the result and explain it a bit. And again, I want to start from this theorem by Lowen and Van den Bergh that served as our inspiration. Sorry, a bit of a cold. Okay, so remember or recall that they solved this curvature problem for the leading example by translating it to the linear setup. Now, what we want to do is we want to consider the class of TDG categories, and we then want to find a class on the right-hand side, which will in general be larger than just linear categories. You can think this through, but if you make it a bit smaller on the left, it should grow on the right. Anyhow, and then do the same thing. So our general theorem will be true for B, a bounded TDG category. And you don't need the boundedness. You can also do this in the big case, and that's, for example, in our preprint, but I'm only going to discuss the bounded setup because it's the ideas are the same and there are way less technicalities. So let me just restrict to this. And as I also said, we will treat all the hierarchical cohomology groups. But if you look to this theorem of Lowen and Van den Bergh, then there are two notions that are very intrinsic to the abelian category theory language, namely the notion of an injective object and of the incompletion. Because you can't really discuss injectivity for an arbitrary object in a TDG category. Okay, and the same is true for this incompletion. So what we need to do first is we need to find generalizations of these notions. Okay, and that's sort of the last bit. So we need to replace the injective by something that holds for any, or that is applicable to any TDG category, and the same for this incompletion. And now I will just first give you the definition and then explain why it's very reasonable, because I thought it would be a bit dry otherwise. So an injective we will replace by a derived injective. Okay, so what is a derived injective? You can sort of view it as a lift of an injective in the heart. We have a T structure, so we have this aisle and co-aisle. And I didn't mention this, but if you take their intersection, you obtain the heart, which is an abelian category in the dB of A, the binary derived category. This is just your A. I think my screen stopped sharing for some reason. I'm sorry. We're back. Yeah, okay. So we consider an injective object in the heart, and then we can look to this functor right here. So it's a functor growing from T up to, in this case, K vector spaces, because we're working with a K-linear abelian category. So we take an object in a triangulated category, we apply this cohomological functor to it, to the heart. So this is this truncation below and above 0. And then we hom into this injective object. Now, if this is a representable functor, then we call the representing object a derived injective. So we can really view this as an object lying above your injective object in the heart. So you take an object, you map it to the heart, you map into the injective, and the representable object will be a derived injective. Note that this might not exist. But, for example, if your heart does enough injectives and maybe this was already there, but Brown representability holds, then this thing here will actually be a representable functor, and this object will always exist. Okay.
And does it have a...
and yeah, you also need... Yeah, go.
Does it have a nice presentation under these conditions? Can you describe explicitly this derived injective?
That's super hard. Yeah. You can do this for certain TDG categories, but in general, what you can say, this is an interesting question, is that it will only have cohomology in positive degrees, okay, and that the zeroth cohomology will be an injective object. But it can have arbitrary high cohomology, and the, even to compute it, it's classic X. Yeah, it's and as general TD things you can. I'm so sorry. Yeah. That my uni is not so good. Yeah, sorry. What I wanted to add, am I clear again?
Yes.
Just so that what I want to add is that there is a realization functor. So you can take the heart of the CDG category and look at the binary derived category or the derived category, but the TDG category will, in general, behave very differently. So we cannot just understand the derived injective by looking at the X on this hard. So it's even for the first or the second cohomology of this derived injective, it will be already very difficult. But it's a very interesting question. And I find it very difficult to think of examples or even understand examples that are not either trivial or too difficult.
Right.
Yeah. Okay.
Sorry, and this is the structure. So this is changed if the structure is generated, let's say, by a shifting object or a co-shifting.
Yeah, exactly. That's also what I'm thinking of. Say you have a co-shifting object.
Yeah.
Sorry, I'm very excited about this because I've been thinking of like the co-shifting object versus pure injectivity for a bit. And yeah, if you ever want to think about this together, but a co-shifting object will be derived injective for the T structure it induces.
Right.
Exactly. Yeah, but then the point would still be, of course, as you know, a co-shifting object does not have to be a complex in general or bounded. It can have, but it will be the case that this co-shifting object is derived injective, so it will at least be bounded below.
Right.
And the injective will be an injective co-generator of the hard.
Right. And the co-shifting object would be a generator of all these derived injectives or not? So.
The only thing I can say is that it will be an injective co-generator, but I don't know whether it generates the category of derived injectives because the category of derived injectives is, I'm not sure that's true.
Okay.
But it's, yeah, I should think about this, but I'm a bit on the fence because this is really interesting and I want to keep it brief, but again, So what I want to say is that the category of derived injectives is in general not graded, but DG. So there will be complexes, the structure of a complex.
Okay.
So it's not just a graded category. If it were a graded category, I would immediately say yes. But that's why I'm being a bit on the fence and I would have to first look at it. But yeah. Does that answer the question a bit?
Yeah.
Yeah, okay, great. But very interesting question. Okay, so yeah, what I should probably say right now is that this definition is reasonable because if you compute the derived injectives of our leading example, where we use the standard T structure, you need to specify T structure. These are just the injectives in the heart, which is good because we want to generalize this theorem by Lowen-Van Bergh. So it should be compatible with their theorem. And so we will replace injectives by dg injective. But then, as I mentioned, if you don't have enough injectives in the heart, or if you're not well generated, so you don't have prime representability, or this H0 does not preserve co-products, then we won't have enough derived injectives. So we need to find some construction that gives us a larger TDG category with enough derived injectives. That should also be compatible with the abelian int completion. Now recall that int completing is actually adding filtered colimits. And so that will serve as our inspiration to generalize to the TDG case. And this theorem was actually the main technical hurdle that I've had when working on this project. Okay, so it goes as follows. If you have a bounded TDG category, or again, we can do without the bound, but yeah. Then there exists a TDG embedding, B to int dg, and we call this a homotopy int dg completion. Because what we're doing is actually we're closing under filtered homotopy dg colimits. Anyway, because this is a TDG category, it has an induced T structure, so it has a heart. And well, it appears that this heart is actually just int completing of the original heart. So this is what I meant by it should be compatible with the abelian int completion. So that's luckily the case. And then it's also good that this thing actually has enough derived injectives. Well, why? It's compactly generated, prime representability holds, and so on. Okay, so then again, I want to say that if you look to, yeah, the int dgq of this bounded derived category, then actually you end up with, yeah, no, put it like this. So we retrieve the unbounded derived category on the int completion. And actually, I will, just in case, put the plus. Yeah, I think this is better. And then we can even do without this. Okay, so as you just saw, I put a plus right there because we will actually have to use this int dgq plus. We will have to restrict to the bounded below part. Why? Because we need non-degenerate structures, and this int dg completion is very, very big. You could actually, it will be usually the homotopy category of injectives of Krause. And that's just too big, and it's bigger than the derived category. And so we need to restrict to the plus to have compatibility. All right, but then we have everything. And then I can actually state the general theorem. So, okay, we have a bounded TDG category, and then the DG Hochschild cohomology will be the same as that of the derived injectives of this homotopy int completion. And thanks to the question, I already mentioned that the category of derived injectives is not linear or just graded. It's again a DG category, so I should put the subscript DG here. And now you can ask, how are we improving the situation? Because we take a TDG category B, associate to it this category of derived injectives. But this is again a DG category. Well, the important bit is that this is a DG category that is cohomologically concentrated in negative degrees, DG minus. Now, curvature comes from positive degrees, specifically degree 2. So there cannot be any curvature when we deform something like this. So again, if we deform, we stay in this dg minus setup, and then we can translate back as before. Okay, so it's very important that this is dg minus. All right, and then as I promised, we can give an interpretation, deformation-theoretic interpretation of all the high-Hochschild cohomology groups in terms of bounded TDG deformations of B along the morphism theta n, going from k epsilon over epsilon squared to k, where the degree of epsilon is 2 minus n. Now note that 2 minus n will be negative or just 0 for n at least 2. If this is negative, then we obtain our original theta, our original base change morphism, and infinitesimal deformations. But if n is 3 or larger, then this will be strictly negative, and this will be a morphism of dg algebras. So it makes sense that we're had to sort of move to the dg world. Yeah, because maybe I should first mention the corollary. And this will be also the last slide. So as a corollary, we are actually able to interpret the higher Hochschild cohomology groups of any abelian category. Because we can, using the result of Lowen-Van and Bergh, move to db dg of A, and there we can, of course, deform along this morphism of dg algebras. All right, and I think that's kind of nice to, also understand these higher groups. And that's all I wanted to say. So thank you for your attention. And I'm very sorry for all these Wi-Fi related problems.
It's okay. Thank you very much. Are there any questions for Julie?
Yes. So I have couple. Sorry.
No.
So the first one, my algebras tend to be very naive. So there are arcing algebras. You have always enough injectives, enough projectives, and so on. So if you have derived equivalence, you have the Hochschild cohomology. It's derived invariant, so you get everything the same, right? I mean, you don't get right. And the other question is less naive, but so you're taking the structure of the D structure as part of your data, and the difference is like essentially the hearts and the injectives in the hearts, right? I mean, this is what makes the difference. How different they can be, right?
Exactly. Yeah. And it's, to me, also not clear whether I feel personally that as soon as you have a good non-degenerate T structure that you understand with enough direct injectives, I think it doesn't really, I mean, the choice matters, but I feel like you can actually see this in here already. We just need one to control the curvature. So I would feel that it doesn't, that most of them will be related, and it doesn't really matter which one we pick. Probably there are some torsion theories at play there, but
yeah, because sitting objects induce some kind of dg equivalent, right?
Sorry. Yeah, the tilting, you mean, that they induce like a dg equivalence.
Not all tilting, or tilting not in general, right? I mean, you're working a very general setup in general.
Yeah.
You need
exactly.
And so on, and this is right. I think I need to be closer to the microphone, maybe, or is it okay? Yeah, and the other question that goes, I mean, which is very different, and do you have you thought about applications to stability conditions? I mean,
No, not yet. Yeah.
Assume that you know the stability manifold of a triangulated category with a bounded structure. Do you get some kind of deformation of the stability manifold or something like that?
Do you get some sort of deformation of what?
The stability manifold.
I would have
to think about.
Manifold.
Yeah.
Oh.
So that means that, and the manifold consists of all these T structures, or?
Right. So the Richland stability conditions of triangulated categories, each one of them has T structures associated to them, bounded T structures associated to them, and sort of you can define a topology. So you have a complex manifold out of all the stability conditions at once, and there is this conjecture saying that this stability manifold is always contractible, for instance. This is an open question. And then I was wondering if deforming your categories might give rise to deformations of the complex manifold associated to them because these stability conditions.
Yeah, but I'm writing it down because it's an interesting question. But I don't know the answer.
I mean, it might be a very difficult question.
Sorry, it might be
very difficult in general. I mean,
I think so. But
quite difficult to.
But still, it would be nice to just Sorry, what was your name? I don't know who in the end asked the question.
Sorry, I'm Hipólito Trefinga. I
didn't hear. Sorry, one more time maybe? Or Najib can tell me later, maybe.
I can type it out.
Okay, thanks. Yeah, maybe also, because you were also the one about the coinciding objects, right?
Yes.
Yeah, I was actually when I was doing this work, I didn't know about coinciding objects.
Oh, right.
But then but then I heard them in a talk by Lydia Angeleri after, and then it sort of immediately the connection was clear. But yeah, but it's
That's
still
my name. I put it on the chat.
okay, great, thank you.
Yeah.
Okay, great, yeah. But yeah, I was hoping that in one direction I could maybe shed some light either on derived injectives or on pure injectives, but it's not so yeah, so far no luck.
Yeah.
But it seems, yeah, what I maybe wanted to say is that as soon as you have a DG enhancement available, the coinciding questions become trivial because like you have exact colimits and stuff in the DG world, but you don't have them in triangulated sense.
Right.
So the question of having a DG enhancement is sort of closely related to it, I would say.
Right. Yeah. Yeah, I work in things similar to Lydia. So, but sort of she works in the realm of module categories or big triangulated categories. I work more in the small world.
Yeah.
Or,
That's interesting.
yeah.
Yeah,
Or building kind of thing.
What I could maybe also say is that it's interesting that that actually here you can only do this for very small ones, so bounded, and then a small with respect to some universe, or very big in the sense that they're really int DG completions. So you can, in the abelian world, you can either have a very small abelian category or a locally coherent Grothendieck category. But the Grothendieck, which would be in the middle, so a Grothendieck TDG category, you can define this, but the deformation story doesn't seem to work well there.
That's very cool.
Yeah, it's interesting, but I'm not sure. I think it's cool yet. Anyway, that's
very interesting.
Thanks.
Yeah.
Great. Are there any more questions for Julie? If not, thank you again, Julie.
Thank you, and thanks again for the invitation and the patience.
It was very nice. Thank you.
Thanks.
Thank you, Julie.
Yeah. Biden, I think, or
before, yeah.
No. I was, yeah. Sorry, I didn't want to.
Yeah.
Stop sharing.
Yeah, before you leave, I got a small comment.